Hello everyone, thanks for coming. My name is Shihao Yuan. Today I will be talking about our work on bridge monitoring using 6-degree freedom measurement. When bridges start to age and deteriorate, keeping them safe through maintenance becomes important. Structural health monitoring, which aims to detect and quantify possible structural defects, can ensure timely maintenance and prevent unexpected threat to public safety. During the past decades, seismic structural health monitoring has grown rapidly as it is a significant alternative to other observational and intrusive methods, which might be costly, time-consuming, and subjective. Conventional seismic structural health monitoring use various sensors, such as geophones and seismometers, to monitor the bridge vibrations, eigenfrequencies, modal shapes, or other indicators for the structural behavior in both space and time. In this talk, I will introduce a new 6-degree freedom or 6-component seismic measurement for structural health monitoring. First of all, what is 6-component measurement? Modern seismic observations are mostly carried out with seismometers, which mainly record 3-component translational motions. However, ground shaking or structural vibrations caused by natural or anthropogenic sources will not only generate translational motions, but also 3-component rotational motions. With the availability of new seismic instruments, we now can record both translational and rotational motions simultaneously and accurately. If we co-locate one traditional seismometers and one rotational sensors, or we simply integrate into a single instrument, that is a so-called 6-component or 6-degree of freedom measurement. Can bridge health monitoring benefit from such 6-component measurement? Before answering these key questions, let's first look at the vibrations of a real bridge. Severe damage may happen during resonant vibrations, which can be essentially seen as standing waves. To formulate a single-mode standing wave, we can sum up two undynamic waves that move in opposite directions. It is easy to prove that the amplitude ratio, denoted by the letter phi, between acceleration and rotational rate is proportional to the wave velocities, skewed by the term tangent kx, which is related to the vibration mode and the position of the 6-component receivers. If we look at a single-mode vibration with a fixed 6-component receiver, the relative amplitude ratio changes is actually equivalent to the relative velocity changes, which might be a good indicator of bridges with damages or prestressed loss. To validate the proposed amplitude-ratio-based 6-component measurement, we set up a real experiment with a 24-meter two-span bridge model. The bridge is equipped with an adjustable pre-stressing system. Together with some static loads and the pre-existing cracks along the bridge, we end up with a controllable bridge that has changing elastic properties due to the changing pre-stressing and static loads. We deploy two 6-component receivers on each spine of the bridge and use a weight drop as our seismic source. Both pre-stressing and loading may lead to elastic property changes along the bridge. Let's first look at the static loading effect. The bottom panel shows the vertical accelerations caused by the repeated weight drop source. We have band-pass filtered 6-component recordings to focus on the single-mode vibrations. In the upper panel, under fixed pre-stressing condition, which is 400 kN, we gradually increase the loads from 0 to 900 kilograms. We can see that the estimated relative velocity changes represented by the black dots using amplitude ratio with sliding windows decrease accordingly from 0 to minus 17%. That is what we expect, since the loading may cause deflections and the opening cracks of the bridge. Next, we would like to test the pre-stressing effect on our 6-component measurement. The bottom panel still shows the vertical accelerations, while the upper panel gives you some repeated patterns because we repeat the weight drop sources and the loading precise. The additional factor we introduce here is the changing pre-stress values. As shown by the different color blocks, we reduce the pre-stress from 400 kN to 250 kN. To separate the pre-stressing effect from loading effect, we can focus on the same static load under different pre-stressing condition. As indicated by the blue numbers and the right dashed line, the estimated relative velocity variations decrease with the decreasing pre-stressing. This is quite reasonable since the pre-stress loss will weaken the bridge, in other words, reducing the wave velocities. Besides, the step-like velocity variation suggests that the loading effect on the bridge property changes might be reversible. So how about the pre-stressing effect? To test if pre-stressing effect is also irreversible, we add back the pre-stress without applying static loads. As is shown by the different color blocks and the right line in the upper panel, the relative velocity changes get back to zero as we gradually recover the pre-stress. The last color block on the right shows a decreasing velocity variations simply because we add again some loads as indicated by the numbers. Now we can see that both loading and pre-stressing may have reversible effects on the material properties, and these effects can be captured by the proposed 6-component measurement. If you take a look at the experiment setup shown on the upper right corner, for the 3 configuration we just discussed, we find the 6-component receivers and the stack loads are always on the same side. What if we put 6-component receiver on the neighboring span? Will the changing stack loads and the pre-stretching cause the same effects on it? For this concern, we apply the same algorithm to the other 6-component receivers on the neighboring span as indicated in the upper right corner. For each pre-stressing condition represented by the color block, the same changing stack loads are applied as before. However, we notice that the relative velocity variations due to the changing stack loads are much smaller than the previous ones, where the 6-component receiver is on the same span of the loads. This is possibly due to the fact that the middle supporters separate the bridge into 2 parts and the stacked loads have a non-uniform effect along the bridge. More importantly, the amplitude-ratio-based measurement theoretically has a near receiver sensitivity, which might distinguish the inhomogeneous property changes. In contrast to loading effect, for 6-component receivers on either span of the bridge, the more uniformly distributed changing pre-stress leads to a similar velocity variations as indicated by the right line. With that, I would like to summarize the proposed 6-component measurement for structural health monitoring. We have shown that the amplitude ratio between translation and rotational motions are sensitive to both pre-stress and static loads related material changes. The 6-component measurement might also help to locate the potential damages thanks to the near receiver sensitivity. In this work, we focus on standing waves for a certain mode. Actually, the amplitude ratio-based method is also applicable to both non-propagating and propagating waves, such as LAM and surface wave. We do have done some validation experiments using synthetic simulations and arrival time-based seismic measurements, for instance, Coda wave interferometry. We do not have time to show here in this recorded video due to the time constraint, but we can definitely discuss during the live sessions. In the end, I would like to thank all members of the dueto project and also the session conveners for inviting me. If you have any questions or comments, you can reach me through the following emails. Thank you all for listening.